So now we've spent a few videos discussing game theory, introducing some game theoretical concepts such as game trees and decision nodes. Now we can actually start understanding a little bit more about solver algorithms and how solvers actually work. And we'll start by exploring what is the goal of an actual solver. A solver's primary goal is to find the equilibrium of any game tree. And we define that as the set of strategies at which neither player can unilaterally change his or her strategy to exploit the others. And that's the definition for a Nash equilibrium, which we've already covered in one of the previous videos. I think it's important to call out that solvers don't actually calculate down to an exact solution for most trees. It'll try to calculate down to a solution for most trees, but it won't actually get there for a lot of cases, especially when trees are more complex. The algorithm will continue iterating closer and closer to an equilibrium point, but the amount of time it would take to actually reach that solution can be very significant in some cases, which could be hours or days or weeks or even more, depending on the complexity of that given tree. What we usually see is that the algorithm is usually stopped after some level of accuracy is reached, and usually that's noted by some sort of percent of the pot that either strategy can be counter-exploited for. We'll get into the specifics of that, but the important thing to note here is that we don't necessarily reach equilibrium in a lot of cases of running solutions. What the solver is actually trying to optimize for, there's a lot of different metrics and data points within solvers, which we'll cover in some upcoming videos, but solvers are trying to optimize for expectation value, or how much money or chips or whatever unit of currency that we're using within that particular game or that particular model. The solver is trying to maximize that for both players. And the solver is going to calculate the EV for every single combination of every single hand throughout every single node of the entire game tree, while adjusting the unlocked strategies of both players with the goal of finding that equilibrium state for both players. The question then comes is how do solvers actually do that? And the way I like to explain this and the way I like to think about this was perfectly explained in Will Tipton's awesome book, Expert Heads Up, No Limit Hold'em. And he introduces this exercise in the second chapter called the equilibrium exercise. And he does so as a way to think about how to develop exploitative strategies. But I think this exercise is actually a really, really great way to conceptually think about how a solver works. This exercise, we start with considering a regular poker situation, and we specify a strategy for one of those players. When we have that individual strategy for that poker situation, we turn and find the second player's best counter response to that strategy. Once we have player two's best counter response for that strategy, we then turn back and find player one's counter adjustment to player two's best response. And then we continue repeating that back and forth, or until we get to a point where we reach a solution, or we reach some type of repeating loop, or we reach a point that is somewhat close enough. And as I mentioned, I think the equilibrium exercise is a great way to conceptually think about how a solver works towards a solution. I'd like to actually walk through an example with you in this video. Let's consider this game tree that we have here. And it's a somewhat simplified game tree here. We're on a river spot, and within this river spot, the hero can either shove for 60 big blinds here, or check. If the hero shoves, the villain here can either call or fold. If the hero checks, now the villain can either shove for 60 blinds or check. And if the villain then shoves for 60 blinds, the hero only option here is to fold. So again, not a super realistic scenario here, but it's a scenario that we can actually work through and manage the math on our own without actually having to open up a solver to do so. What I did here was I wanted to try to actually give us some form of realistic ranges and a realistic scenario for us to work with here in this situation. We're going to assume that this situation actually started with effective stacks of 90 big blinds. Pre-flop, our villain our opponent here raises the 3 big blinds from the button, and our hero here calls from the big blind. And for simplicity here, we're just going to assume a dead small blind here. So we get to a flop where the pot is 6 big blinds, and the flop is queen 10 6, where the queen and the 6 are hearts, and the 10 is a diamond. Now, hero checks, and the villain bets a third pot of 2 big blinds, and hero raises 4.5x to 9 big blinds, and the villain calls. The turn here is the 2 of spades, where the pot is 24 big blinds, and the hero bets 3/4 pot, and the villain calls. And that leads us to this river 3 of clubs, where the pot is 60 blinds and we have 60 big blinds left on the river. So we're only giving options here to bet a full pot size bet for both players in the river. So we're not giving the option here to bet smaller, or in this case here, if villain actually does get to this shove portion of the tree, hero is always folding here too. So hero actually doesn't have an option to call. And we also have to look at some ranges here on the river. So I tried to keep these ranges close-ish to what might actually happen in this given hand. We'll say that hero gets to this point, and after the hero check raises this flop and continues betting on the turn, hero is going to have some sense of some type of value here. So, they're going to have some straights, right? So in this case here, exactly 1 straight. So hero would have raised here, check raised on the flop here with 5-4 of hearts, and got there with running 2-3 to get the straight. Hero also raises here on the flop with some value here. So pocket 6s, queen 6 suited, 10 6 suited, queen 10 offsuit are 2 pair. Hero check raises on the flop and continues barreling here with some open-ended straight draws. So we have 3 king jacks with the king of hearts in this spot here, and then a bunch of different flush draws here. So overall, hero has 32 total combos in his or her range. Our opponent here, our villain, also has some hands in his or her range. Remember, villain is the original aggressor, so villain has this pre-flop uncapped range. Villain's gonna have value here in this spot. So, villain is going to have the 5-4 for the straight. Villain's gonna have sets, so queens, 10s, and 6s, queen 10, queen 6, queen 3, queen 2, 10 6 for all of these 2 pair plus combos. Villain is also going to have some overpairs, so aces and kings. Villain has a lots of queen X in range, so ace queen, king queen, queen jack, queen 9, queen 8 suited, queen 7 suited, queen 5 suited, queen 4 suited. Villain also has a lot of flush draws that also have pairs, right? So these busted flush draws like ace 10 of hearts, king 10 of hearts, jack 10 of hearts, all of these that pair the 10. And then some of these flush draws here that paired the 2 or the 3. So, like ace 3 of hearts, ace 2 of hearts, king 3 of hearts, king 2 of hearts, etc. And then a bunch of these other missed draw hands. So some of them being flush draw, ace high flush draw hands, some of them being missed straight draws. But I think this is somewhat of a reasonable range for villain to end up here on the river with. But overall, hero has 32 combos, villain has 180 combos. And this is kind of indicative of a polarized range from check raising the flop and then continuing on turns and rivers versus a somewhat uncapped range, but largely a lot of bluff catchers in this range as well too. So, and then a lot of missed draws in this range as well too. So 180 combos here in villain's range. Hero's overall range has 59% equity against our opponent. The villain has 41% of equity. And how that would actually work out if both players check down on the river here, hero would be entitled to 35.5 big blinds in the pot, and the villain would be entitled to 24.5 big blinds in the pot. Hero is folding his entire range to a villain bet after checking, and since that's the case, we only need to focus on one strategy, which is hero's shoving range. And the villain only needs to decide on calling a range to a shove. Since hero's always check folding, villain should always be shoving and going all in when checking 2 on the river. So for this initial baseline, and that's the first step in this equilibrium solution, we're going to assume that villain is going to call with all hands that can beat a bluff. So any ace high hands are better. And, we'll say whether that's realistic or not, but that's the assumption that we're going to make, is that villain's going to call with all hands that can beat a bluff, ace high or better. And again, it's important to note here that if the river's checked down, hero is going to win 35.5 big blinds on average, which is that from that 59.1% equity, and villain is going to win 24.5 big blinds on average, which is the 40.9% equity. So let's start with iteration number 1 here. And we have here this range that villain calls all of these hands with showdown value. So anything ace high or better, that's what our opponent is going to call with. And what we want to know is, what is the range at which the hero should be shoving in this case here? Well, we can figure this out by plugging all of this into equity calculators here. And what we find is, if villain is calling with all of these hands, hero's best response is just to simply shove with value and check fold everything else. So 2-pair and better, and checking folding everything else. So of the 32 combos in hero's range, hero is going to fold all of the bluffs and shove with value. So they're shoving half the range and folding and check folding half the range. And hero's shoving range here is the 5-4 of hearts, pocket sixes, queen 10 off, queen 6 suited, and 10-6 suited. And by taking this exploitative line, hero's expectation is to make 42.7 big blinds. So that's greater than the 35.5 big blinds that we'd expect if we just check this down. Because villain is calling with such a wide range, hero shouldn't bluff, and hero should really only bet strong value hands and take advantage of the fact that villain is calling with such a wide range. So we have this first range here that hero is shoving with. And the second step of this process is, now we flip this and we turn this around and look at what the villain's best response to the hero shoving range looks like. If hero shoves with value, so 2-pair and better, and check folds everything else, they're shoving with this range of 16 combos. And what we want to find now is, from the villain's perspective, what are the hands that villain should be calling with in this spot here? Well, now if we know that hero has this very tight shoving range and is never bluffing, now villain folds everything worse than top 2-pair. So villain's actually even folding some of the 2-pair combos in range. And instead of calling with over 100 combos in range, now villain's calling range has whittled down all the way to 19 combos. They're only calling with the nuts, the 5-4 in this case, or sets or top 2-pair. And then now in this case here, hero's expectation value now drops all the way down to 27.4 big blinds. If hero has no bluffs in range, villain can exploit the hero by just releasing hands, even hands as strong as queen 6 suited to a shove. Because remember, in this specific game here, if hero checks, hero's always check folding. So villain can just shove all of those bluff hands now if hero is checking. And if hero's shoving, the villain knows that the hero is only has value. It's devoid of bluffs in that range. So now we're going to flip this again, and we're going to say, if villain is only calling with this range, what is the best response for hero? And what we find here is, now if villain has this super tight range, well, now it's profitable for hero to shove with everything in range against this villain's tight value calling range. Hero's EV skyrockets back up to 50.3 big blinds. So by shoving every hand in range in response to a very tight opponent's calling range, hero's just going to take advantage of the fact that villain is folding far too much in this case here. So villain is way over folding, and hero's going to be making money that way. We're going to take a couple more iterations at this, and let's take a look at iteration number 4. So now if hero is shoving with everything in range, what should villain be calling with? And what we find is that now villain is going to have a range that's more similar to the first range, but not exactly quite as wide as that first range. So villain calls with most pairs, but actually folds some. Villain folds pocket kings with when it has the king of hearts. And it also calls with some ace high hands, such as ace of hearts, jack of hearts, or ace of hearts, 4 of hearts. So what we find here is that blockers are key for some of these close decisions here. If villain has the king of hearts in range, that's going to block a lot of these bluff combos. So king 8 of hearts, king 7 of hearts, king 5 of hearts, king 4 of hearts, king 3 of hearts, king 2 of hearts. Having the king of hearts in range takes 1, 2, 3, 4, 5, 6 bluffs out of our range. Actually, 9 bluffs out of our range if we include these king jack offsuit hands too. So by taking 9 bluffs out of range, we've already tilted us back towards value. So by having the king of hearts in range in this case here, it's a bad card to have for villain, in which case villain should be folding these hands. Other hands like ace of hearts, jack of hearts ends up making good calls, because in this situation here, having the ace jack of hearts, it doesn't necessarily block a lot of villain's bluffs. It only blocks several of these bluffs. So these close decisions, blockers become very, very key for these close decisions in this spots here. So Hero's EV goes back down to 32.1 big blinds, which is less than the 35.5 big blinds if it was checked down. Villain calls more widely before to account for Hero's additional bluffs, but not as widely as in iteration number 1. So we'll do this one more time, going back to iteration number 5. If we have villain's calling range, what should Hero be shoving with? And what we find is that Hero should be going back to shoving with the same range from iteration number 1. And Hero's EV goes back up to 40.8 big blinds against this wider calling range. You can no longer profitably bluff and goes back to shoving with only value hands in range. Now, we can continue going back and forth for a long time, but what you'll see here is now that we've gotten back to this first point, we've kind of reached this loop. If we went to iteration number 6, it would be the same thing as iteration number 2 for us. If we went to iteration number 7, it would be the same thing as iteration number 3. And they can go back for a long time, and sometimes we'll find the true Nash equilibrium this way, but others, including in this example, we're going to end up in a repeating loop where we never really reach a steady equilibrium point. And strategies can change significantly when both players are trying to exploit each other. Sometimes the adjustments that you see are really not that intuitive. So folding kings in that spot there is not that intuitive, while at the same time calling ace high is not that intuitive. Now we can estimate the true equilibrium in this situation here is probably somewhere between iterations 4 and 5. We can estimate the EV probably fits somewhere between those range. And, if we wanted to, we could find the exact value. We'd have to employ a little bit more complex math, including mixing some hand combos, which, we'll get plenty to mixing throughout later modules. But, as you can see here, this is a fairly simple example, and the math is fairly complicated for us to do on our own. Now, this is where solvers come into play. Solvers can mix hands and mix individual combinations between the strategic options far more efficiently and far more accurately than we can. And they can better balance ranges that way. And by doing so, they find points of indifference between those two strategies, which helps them come closer to finding the game's true Nash equilibrium. Now, it just so happens I actually did run this through a solver to show you what a solver solution would actually look like. And because this is a simple river calculation, we actually can find a Nash equilibrium here. What we find here is that the EV, if we do get to a Nash equilibrium, it is between those two iterations that we proposed. And the true expectation at equilibrium is that Hero shoves with 22.4 combos and earns 36 big blinds of EV. This is what the Hero's shoving range looks like. The shoving range is in blue here, and it includes the value that we expected, right? So the 5-4 suited for the straight, and includes the 2 pair and better, so the set of 6s, queen 10, queen 6, 10, 6. But it also includes some weaker pairs. The solver is shoving all of ace 3 and ace 2 of hearts, a portion of king 3 and king 2 of hearts. It's also shoving some of the weakest bluffs, hands like 7-5 suited, 8-5 suited, most of 9-7 suited, and then some of king 4 suited. And if you can kind of see this tiny sliver up here, it's also shoving a little bit of ace 7 suited as well too. Villain's equilibrium calling range is just about 78.7 combos, and they're earning an EV of 24 big blinds. And what you'll see here is that this range includes all the 2 pair or better hands: Queen 10, Queen 2, Queen 3, Queen 6, 10 6, pocket 6s, pocket 10s, pocket queens, 5-4 suited. All of them are calling. But Villain's actually now folding all of the overpairs in range. Villain's calling with most of the Queen X hands, but you'll notice here that the Queen X hands that it does fold are Ace Queen and King Queen, specifically if the hand contains the Ace of Hearts, because as we've mentioned, those are the cards that are also going to be blocking bluffs in our opponent's range. And then finally, it's also calling exactly Jack 10 of hearts here too. So an interesting calling range here for Villain. It's calling Jack 10 of hearts while folding aces and kings. And you can kind of see the blocker effect here at what we find at the equilibrium. So how does that equilibrium exercise relate to solvers? Well, while we can actually try to calculate this simple river game tree by hand, and as you can see, this was fairly complex. I actually, did a lot of the calculations of this through a solver, while you can also do this using equity calculators. But this one is actually fairly complicated itself to get to manually. We'd actually be unable to do so if we're faced with a more complicated tree. And as the size of a game tree increases, humans just can't efficiently and accurately execute the math that's required to calculate all of these game trees. We can see conceptually here, though, how a methodology such as this one in the equilibrium exercise can be executed at a greater scale using technology. So if we had to iterate something hundreds of times or thousands of times at a much larger scale, we can't do that, but technology can. And that's how solver algorithms work, and that's why I wanted to go through this exercises. Solver algorithms are based on some of these similar methodologies. It starts with a strategy for one player and then calculates the response from another player and iterates back and forth until the solution is reached. The computing power that allows solvers to incorporate more complex algorithms and mix at fractional levels helps it come closer to finding an equilibrium than we ever could. Now, solvers can calculate exact equilibrium solutions for simpler game trees, such as this one. I ran this through a solver and it instantaneously got to a solution which is the perfect Nash equilibrium solution for that particular game tree. But as the complexity of that tree increases, the amount of computing power necessary to find a Nash equilibrium increases significantly. And as a result, as I mentioned before, solvers will just continue iterating until the maximum exploit either player can take against each other's strategy is usually within a designated amount. Usually we note a portion of the pot that we are comfortable with being exploited for in either direction, and we stop the solver solution at that point, or when a time limit is actually reached. The point here is that solvers aren't really solving the hands. They're working their way down to a solution, and they're going to slowly try to get to a solution, but at the end of the day, they're approximating the equilibrium point of a simplified abstraction of a significantly more complicated game tree that we've created that really just has a bunch of incomplete information. And we'll get into some details when we actually get into the inputs and outputs in the next video, but that's the point I want to come across within this video here, is that the solvers are working down towards a solution, but they're never actually reaching a solution for the large majority of scenarios that we construct. And I want to really hammer this point home as to how big and complex game trees can be, because game trees can be huge. I want to look at our game tree in the context of the overall picture, right? So we really looked at this game tree here. We looked at the game tree of the shove from a hero, and the villain could either call or fold. But we had other options here, right? So we could have built out a checking range here and seen what happens if we check, and if villain shoved, we could have given some call or fold option. And I've noted that here by looking at this symbol here. So this symbol represents that there could be other complex points of this game tree. So if we checked here as our hero and villain bets, we could also decide that we want to have a calling range and we want to have a folding range here. So there could be portions of this game tree that we can explore, whereas these other circle points represent endpoints of the game tree. If we work our way back further, we know that that was just one of 48 different unique river cards that could have come in the deck. And any one of those river cards changes the range that we would have and what each portion of our range would do at each part of that game tree here on the river. And we'd have a bunch of different actions that we could take on turns here. So I've highlighted in blue how we got to the river, but there's other things that could have happened. We could have decided to check the turn. When we bet the turn, our opponent could have raised the turn, which would have led to a different portion of the game tree. Prior to the turn, there are 49 different turn cards that could have come, as opposed to just that 2 that showed up on the turn. On the flop, there's a lot of different actions that we could have taken on the flop as well too. So again, we check raise the flop, which was called by the opponent, but we could have bet the flop out. The flop could have gone check, check. We could have just decided to check call the flop. So there's a lot of different things that could have happened on the flop as well too. And if we started from pre-flop, there's 22,100 unique flops that could have come on the flop as well too. So there's a lot of different flops. And there's a lot of different things that could have happened in pre-flop. So what you see here is that the game tree is massive. And as we get further and further away from the river, there are so many different points of the game tree that the solver has to account for and solve every portion of that to calculate a full solution. That's why it takes so long to reach a solution. And that's why sometimes it can't reach a solution. I hope that puts into perspective really, really how big a game tree can be, because I've noted a lot of these different kind of branches throughout the game tree where I can't really visualize all of this. If I tried to visualize every single node of the game tree, I would never be able to fit this on one slide. It would take many, many, many different slides, and it would be really, really difficult to capture. And that's really kind of to show the sheer complexity and size of the overall game tree. So as we attempt to model any scenario that starts further and further away from the river, that complexity and that size of the game tree, as it increases so much more so, it decreases our ability to yield a perfect solution. I want to wrap up this video by talking about our goal of using solvers. We know that we can't reach a precise equilibrium for the most part. So while we can't reach that, we should understand that even if the technology does reach a perfect solution, the output that we get is limited somewhat because it's based on that limited set of inputs that we provide. If our inputs are off, then our outputs are going to be off. What we need to understand is having that understanding of inputs and outputs, and more importantly, how variations of the inputs affect the outputs. With all of that known, we can start devising tests to answer just about any question we have in this game. But we have to have the understanding that the outputs are going to be limited, and it's going to be based off of the inputs that we actually put in. So in order to use a solver for this type of work, we need to have a very thorough understanding of those inputs and a very thorough understanding of the outputs and how we might manipulate them. And then finally, where our own biases will impact the inputs that we enter, and then how we can actually compensate for that bias. The final point I'd like to make with this specific video is that using solvers well, it really starts with understanding the mechanics. Solvers don't have the answers by themselves, but by understanding how to use them and how to vary inputs to measure changes in the outputs, you're going to be able to find the answer to just about any question that you want to find the answer of. And that's going to segue nicely into the next video, where I'm going to look at the various inputs and outputs that we can explore via solvers. So I'll see you then.